Hi, and welcome to my talk. In the next 20 minutes, I will talk about a paper that we recently uploaded to the archive, where we reconstructed the history of the structure growth using different large-scale structure and data sets and also CMB lensing data. I am Carlos Garcia-Garcia. I'm a postdoc in the University of Oxford, and you can find this paper in the archive looking for this reference number. These people listed here collaborated with me in the process of producing this work. So the main goal of this project is to address the S8 tension in a different way. The S8 is a parameter that measures the granularity of the universe, and it is given by this formula here, where sigma 8 is the variance of the perturbations at a given scale. So it basically measures the amplitude of the perturbation. So when KiDS and DES report a value that is lower than the Planck's one, basically what they are saying is that large-scale structure data seems to prefer a smoother universe than the one inferred from CMB. Our idea in this project is to use the information that large-scale structure data have about the evolution of the perturbation. In fact, what we did is to decouple the background and the growth evolutions, so that we let the data to choose they prefer growth evolution. Here on this plot, I'm showing the main result of the paper. In the vertical axis, we see the S8 parameter versus offset, where the temporal evolution is given by the sigma 8 parameter. So on the amplitude of the perturbation, that's what is going to evolve on time in this plot. In the horizontal axis, we have the rest. We see in the top panel that for different combinations of different data sets that I will introduce later, you see that the S8 parameter is lower than the one predicted by Planck. If we move to the lower panel, we see that this tension is driven by shear, and that when we remove shear, we don't see that tension. So let's move on now to see how we have produced this result. First of all, let me introduce the data we have used. We have used data from 5 different surveys, and the main goal of the paper is to do a full data set analysis. So we put all the data together and see what we obtain. But not only that, we were also interested on doing a study that was more similar to KiDS and another more similar to DES, just to address the different levels of tension that they find. So we split the data into different datasets. The one we call North dataset, that is composed by the DESY legacy survey, galaxy clustering, KiDS quick lensing, EVOS quasars, and also Planck CMB lensing. In the South dataset, that is the one that resembles more DES, we have DESY1 galaxy clustering and quick lensing, EVOS quasars, and Planck CMB lensing. You can see on the plot on the bottom the footprint of these different surveys. And you can see that there is no overlap except for the EVOS and legacy survey footprint. But this is only a projected effect. If we go to the recipes, we see that there is no overlap on receipt between the EVOS sample and the legacy survey sample. So let's move to the picture on the right. Here I'm plotting the receipt distribution of the different datasets versus receipt. On the top panel, I'm showing the receipt distributions for the South dataset, and in the bottom for the North dataset. As you can see, we cover the range between receipt of 0.2 to and a little bit. And you see that what EVOS is giving us is something that we constrain the growth at early times. Furthermore, we see that EVOS quasars do not overlap with galaxy clustering from DS nor the legacy survey. So in the end, we have the North dataset and the South datasets that will be statistically uncorrelated. So we will be working with projected data on the sphere of the sky and in Fourier space. So we will be working with the angular power spectra of 2 tracers that we call A and B. That is related to the 3D power spectra with this integral along the pathos side, where the Q's are the kernels, different weights that we give, depending on the kind of traces that we are correlating. Here on the plot on the right, we saw the relation between the receipt distributions and the kernels. the recent distributions are on the top panel and the kernels on the bottom. We see that in the case of galaxy clustering, the kernels follow the same distribution as the recent distribution. This means that galaxy clustering will give us information only about the evolution of the perturbations at those specific recipes. However, in the case of weak lensings, weak lensing is an integrative effect produced by all matter between the source galaxy and us. We see that the kernel distribution are moved towards lower values of recip, and that they will become important below recip 0.5. Finally, we can see this dotted red line that it belongs to the CMB lensing, and basically this tells us that CMB lensing will correlate with all the other data that we are putting together here. Going a little bit more in detail about the different tracers that we are using, we can see that galaxy clustering is a bias tracer, and we model this bias linearly, like in the DESY1 analysis. In the case of equations, we have to introduce as well the magnification bias. Weak lensing tracers are unbiased, but we have to take into account a multiplicative bias and also the intrinsic alignments. And the intrinsic alignments model is the same one as in the DESY1 analysis. Furthermore, we also have to take into account the uncertainty on the reconstruction of the recip distributions. And for that, we allow an extra parameter to vary in our MCNCs that will move up and down the recip distribution in the MCNC. And all these theoretical power spectra will be computed with the core Cosmology library. So that's the prescription for the theoretical power spectra. But now we have to estimate the power spectra from the data itself. So the idea and one of the key points of this paper is to analyze all the data that I presented through a same pipeline, so that we can do it in a consistent way and taking into account all the correlations between all different data points. This is not a straightforward thing to do, and it took us like 1.5 years. And we have different papers in between. The base code is Namaster that is in charge of computing the correlations of the maps from the maps of the different fields, and also the Gaussian covariances of the different power spectra. The pipeline starts from the catalogs. We download the catalogs and apply the same cuts as in the collaborations. Then we produce some maps that we feed to Namaster, which will return us the power spectra of the different tracers. In this process, we found that we had to improve the way we were handling the shear, and Andrina Nicola found a very convenient, so it has this paper showing how we work with the shear, and in particular, she shows that the power spectra of the noise of the shear can be estimated analytically. That means that we don't have to rely on simulations, saving us a lot of time. Once we have the CLs, we can compute the covariance between the different power spectra. And this covariance is computed with a master, and analytically, using the approximation that was introduced first in this paper, and then improved by Andrina Nicola in a follow-up paper, where she improved this approximation for the case of shear, which is much more complicated because of the way you weight each of the pixels. Each of the pixels. So in the end, we end up with 1,275 data points. That means that we have a lot of data, and this will be the main reason why we have so good constraints on the stage, as I will show you later. Once we have all this data together ready, we build the likelihood. We implement our likelihood in MontePython, and we approximate it by a Gaussian likelihood based on the central limit theorem, where the different CLs are a vector array of all the CLs one after the other, of all the auto and cross correlations. The covariance here will be only the Gaussian part of the covariance matrix. In large scale structure, you have 3 different components of the covariance, 1 Gaussian and 2 non-Gaussian. But we have shown that the non-Gaussian parts have a negligible effect on our posterior distribution, so we just restrict ourselves to the Gaussian part. Finally, we apply some conservative scale cuts so that we don't have to care about baryonic effects or non-linearities that our simple simple systematic modeling does not take into account. For instance, if you want to check a paper about how you can do better with a better galaxy bias, you can take this paper from Borean and Hajiska, who took data from our pipeline when we were in the process of building it, and in particular from the DESY1 galaxy clustering with lensing, and she used the much better galaxy bias modeling, and she was able to reach the Kmax of 0.6 inverse megaparsecs. And in doing so, she found 30% better errors on omega matter. We can see here on the right an example of the covariance matrix, where you can see that although it is mainly diagonal, you have some off-diagonal terms that are important to be taken into account correctly if you don't want to bias, if you want to have accurate results. And that's the part where all papers, these two papers, enter. So let's move now to the validation. So first thing we have to do after producing all this data is validate that it makes sense what we are obtaining. So the first thing we did is to check that the B modes are compatible with zero. And that's true, the B modes are compatible with zero. Furthermore, we check that we find compatible results with those from the official papers. And we can see here on the bottom the plots of S8 omega matter, and we see that they are compatible. In black, we are showing the official results, and in pink and red and blue, our results. You can see that there are some discrepancies, but the main reason are different modeling and also different scale cuts. For instance, we have much looser constraints on omega matter because our scale cuts on the clustering are much more conservative. However, we find slightly better constraints on sigma on S8 because we go a little bit higher on L than the collaborations and on weak lensing, and that helps to constrain better SA. Furthermore, we checked that the residuals for the best fit model of the full dataset run followed a Gaussian, and you can see it here on the right. And we not only that, we checked that all the chi squared were meaningful for all the 12 runs that we did just for lambda CDM. And we found that the p-values between 0.1 and 0.9. So basically, we found really good fits. And just an idea, this means that the lambda CDM model fits the data well. Although you can have this discrepancy with the prediction from Planck, but the lambda CDM model fits the data well. So what do we find for lambda CDM? For lambda CDM, we find that the south dataset, the one that resembles more the DESY1 analysis, and the north dataset, the one more KiDS-like, agree. And you can see that both on the plot on the bottom as on the right. On the right, furthermore, you can check that what is driving the tension is actually shear. Here, I'm plotting on the vertical axis all the different combinations that we run on our paper and the results for SA. And you can see that once you remove shear, these 3 points, everything agrees with Planck. That is the gray band. However, when you introduce shear, you find results that are in tension with Planck. If we combine all this data, we are able to shrink our errors by a factor square root 2, meaning that we find an error for SA of 0.0095 and a tension with Planck of 3.5 sigma. Since we have all this data, we are able to have very good constraints. And in fact, if we compare our results with those from other people, we find that our results are the best constraints at the moment. In fact, they are 25% better than those from Planck 18. You can see here on the plot my results on red versus results from other people. And you can see that the results from all the different large scale structure surveys agree with ours. So we find something that is consistent with all the previous results. So let's move now to the real goal of the paper, because we didn't want to analyze lambda in detail, and for that we will have to do a much more careful analysis of scale cuts, baryon effects, and etc. we were interested in reconstructing the growth. So we wanted to put constraints on this S8 offset, where the temporal evolution is on sigma 8, so on the amplitude of the perturbations. And we do this analysis by decoupling the background and the perturbations evolutions. So we keep the lambda CDM background, but we modify the power spectra that we use to compute the CLs by this formula. Here, the linear growth factor is given by a quadratic spline, where the different nodes are allowed to vary in our MCMC. We can see here on the right, on the top, I'm plotting the kernels, and on the bottom, a reconstruction of the S8 parameter, where the nodes are. The nodes are marked by this vertical dashed line and are located at the peaks of the galaxy clustering distributions. And this is to maximize the information that we can take from this data. We check to add some more nodes and move them a little bit, and we found consistent results. We also check, as we can see on the plot on the bottom, what happens if we modify the spline that we are using. And you can see that on the range of recipes where we have data, all results are compatible. They are not altered, almost altered. However, when you go out of these recipes, you are extrapolating, and then it really depends on the spline type that you are using. So you cannot trust what is at recipe 0 in our results, but you can trust what is on the range of recipes that the data covers. So between 0.2 and 2. So let's go to the results. This is the same plot I showed on the beginning, but I will try to go a little bit more slowly on it. So on the vertical axis, we have the S8 offset with sigma 8 having the temporal evolution, so the amplitude of the fluctuations, and on the horizontal axis, the rest. On the top panel, we have the different combinations of data that we already know: the south dataset, the one that is more DS-like, north dataset, the one that is more KiDS-like, and the full dataset analysis that is everything together. And in blue, we have Planck. We see that for both for all cases, we obtain a value of S8 between the recipes 0.2 and 0.5 that is lower than the one predicted by Planck. If we move to the bottom, we see that this tension is driven by shear, and that when we remove the shear on gray, we don't see that tension. Furthermore, we can comment on this huge error that we find here. This is motivated because we have removed clustering in the case of we analyze the green contours, and we have removed the EBOS quasars. So basically, this is telling us that we need those quasars there to constrain the growth at that time. Just as future work, we would like to do a few things. First of all, we would like to add more data. We would like to add data at recipe 0 so that we can trust this area here, as well as recipe 1. At recipe 0, we could use this full sky service like the 2-mass photometric recipe survey or the TSZ. And at recipe 1, we could use the galaxy clustering and quasar. This would be particularly interesting to address this, to see if this kink that we see in the north dataset is meaningful or is just a statistical fluctuation or something from the splines. Also, we would like to generalize the way we reconstruct the growth by using Gaussian processes. And we could also improve the way we handle the systematics by using different models for galaxy bias, baryonic effects, or different models for intrinsic alignments. In addition, we could add massive neutrinos that we didn't take into account. In our analysis. So just to summarize, the key ideas of this talk and this paper are the following. First, that we have already a lot of data from large scale structure that we can combine together to reduce the errors substantially. Furthermore, this large scale structure data is able to inform us about the evolution of the perturbations, and that we can use that information to reconstruct the growth. The tension that we see at recipe 0 is mainly driven by the recipe range between 0.2 and 0.5, where the current data have the best statistical power, and that this tension is driven by shear. If you want to know something more in detail, you can go to the archive and follow this reference, or ask me in any moment during the conference or at any other point of time. I hope you enjoyed the talk, and I hope to see you all during the conference. Thanks.